Hello, welcome back to the channel. So let's do one more word problem on differential equation. And in this question, we have been given that there is a cylindrical water tank which has a radius of 3 meters and height 6 meters, and it's full of water, but the bottom is punctured right now. So if the bottom is punctured, you know that the water will be coming out from the punctured hole from the bottom. And we also have been given the information about the hole, that the hole has a radius of 1 centimeter. And now, if h of t is the height of the water in the tank at t, so you can clearly see that your h is a function of time, right? Which is also understood because we have a punctured hole, so the height of the water in the vessel, the cylindrical vessel, will be decreasing, right? With respect to time. So as time increases, we know that h of t will be, the rate of change of height will be negative. And we have also been given that the velocity of the escaping water from the bottom is a function of time, which is given by v of t, where our v of t is equal to root 2 g h of t. H of t is again the height of the water in the tank at time t in meters. So now, based on all this given information, we have to calculate how long it will take for the tank to be empty. So now, before solving this question, we have to first understand the context of this question and the idea behind how we will be able to find the differential equation, because we first have to find a differential equation in order to get a function of h in terms of t, right? Because we have to calculate the time when the tank will be empty. So the time when the height of the cylindrical vessel, the height of the water inside the cylindrical vessel is 0, right? So that is why we have to set up a differential equation in terms of h and t, right? So now if we have a visualization of what's going on, is you have a cylindrical vessel which is of height 6 meters, and the radius of the cylindrical vessel is 3 meters, which is given. You know that this hole is of radius 1 meter and the water is coming out of the hole from the bottom, right? So now the basic idea about setting up the differential equation is, we know that the amount of water which will be coming out of the hole, or precisely the volume of the water which will be coming out of the hole, would be equal to the volume of the water which is being taken out from this cylindrical vessel, right? So that is the basic idea about setting up the differential equation. We know that the volume coming out of the hole is equal to the volume which is being reduced from the cylindrical vessel at the same time. So now if we want to calculate, let's suppose there is a decrease in height which is dh. So we know that our dh would be negative because it's decreasing. We know that if we are able to calculate this volume decrease, which is caused by our dh decrease, and equate it to the volume which is increasing over here from the water coming out of the hole, if we equate both of these volumes, we'll get the differential equation, right? And we already know about the volume of the cylinder, which is equal to pi r square h, right? So if we have to calculate the volume change, if you have a dh height difference, the volume change in this case, because the volume is decreasing for the cylindrical vessel, your volume is decreasing, right? Because your dh is negative. So your dv would also be negative of pi r square dh in this case, right? I hope that makes sense. Feel free to comment down in this video if you have any doubts regarding this equation over here. So this is the change in the volume of the water which is caused by this dh decrease in height, right? And we already know the radius of the cylindrical vessel. The radius of the cylindrical vessel is 3 meters, which has already been given. So your dv in this case would be minus pi 3 square dh in this case, right? So this is the volume of the water which is being decreased from the cylindrical vessel. So now we have to calculate this increase in volume of water which is coming out of the hole, and we'll equate this dv with this dv over here to find the differential equation, right? Because we know that the volume of the water which is being reduced due to the dh height difference, the same volume is being increased at the bottom of the cylindrical vessel, right? So in order to calculate this dv, we know that the velocity of the escaping water at time t is a function of time, which is also given by this equation over here. So we know that the velocity of this escaping water is root 2 gh over here, right? So if the velocity of the escaping water is root 2 gh and we have to find dv, in this case we also know that dv is again pi r square. So this is a different radius, so I'll denote it by r dash. So pi r dash square, where your r is the radius of the hole, which is already given as 1 centimeter. So you know that this radius, this r dash is 0.01 meter, because we are taking every unit in meters. And in this case, since you're calculating the volume change, you know that the volume of the cylinder which is being formed in this case would be pi r square h. Since you are calculating the small change in volume, so you'll have dh dash over here, right? Again, I'm using h dash, not to confuse it with the h that we previously used. So this h dash is basically this height over here, which is being increased. So now in order to calculate this, dh dash, we'll use this equation over here. We know that distance, that's denoted by x, is velocity into time. So for a small change in distance, dx will have v dt, right? That is what we already know about distance and time equations, right? So now in order to calculate this dh increase, we can change this equation as simply, so in this case our x would be h dash and it would be v dt in this case. And we already know what our v is. Our v is basically root 2 gh. So our dh dash in this case would simply be v is root 2 gh and dt would be dt simply. So now this dh dash is basically the increase in height of water which is coming out of the hole. So now we can plug in all the values that we calculated so far into this equation to find the change in volume. So our change in volume, which is the increase in volume over here at the bottom of the cylindrical vessel, would be simply dv equals pi times 0.01 square, because our r dash is 0.01. R dash is basically the radius of the hole. So 0.01 square times dh dash is simply 2gh times dt in this case. And we know that the volume which is being decreased from the cylindrical vessel is the same volume which is getting increased under the cylindrical vessel. Or in other words, the volume of the water which is being decreased from the cylindrical vessel is the same volume of water which is coming out of the hole, right? So this dv is equal to this dv, and if we solve this, we'll get simply minus pi 3 square dh, which is over here, minus pi 3 square dh equals this dv over here, which is pi times 0.01 square times 2gh dt. And now you can clearly see in this expression that you only have h and t variables, and you also have a dh by dt term. If you shift your dt to this side, you have a dh by dt term. So you can easily solve for this differential equation and get h as a function of time, right? Get h as a function of time. And we also know about the initial condition, that when our t is equal to 0, which means when our water was just about to come out of the hole, our height was 6 meters, right? So we have an initial condition as well, that h of 0 is basically 6 meters over here, right? So we can use this initial condition to calculate for a constant of integration as well. And if you'll solve this, you have this differential equation over here, right? So you have this differential equation. If you'll solve this differential equation, this would be a similar separable differential equation, and you'll get this function, this h representation in terms of t with a constant of integration, and then we'll use this initial condition to calculate the value of the constant of integration. So this will be your final function h in terms of t. And now in this question you had to calculate how long it would take for the tank to be empty, which means your time value when your h is 0. So you can simply plug in h equals 0 in this equation to solve for t, and if you'll solve for your t, you'll basically get 27.66 hours as your final answer. But the main important point about this question solution was basically identifying how to get the differential equation. And in this question, we identified this pattern over here, that the volume which was being decreased from the cylindrical vessel was the same volume of the water which was coming out of the hole at the same time, right? So this was the basic fundamental concept that we used in order to first set up a differential equation and then solve for our h as a function of time in this case. So that's it for this video. Feel free to comment down on this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.